If an object is moving with constant velocity, that means it's moving in a straight line at a constant rate. Its path through space would look like this straight dotted line on this graph of y versus x. This is a map of its path through space. Let's say it started right here at time t equals 0. So its displacement vector points in this direction, and therefore its velocity vector will be parallel to that displacement. It's pointing in that direction also. Now, if it is moving in a straight line, the distance it's traveling is going to be exactly equal to the magnitude of its displacement for a straight line path. Therefore, its speed, the distance over time, is exactly equal to the magnitude of the velocity, which is the magnitude of the displacement over time. Speed is equal to the magnitude of the velocity in this case. We often think of speed as being the magnitude of the velocity. They're exactly the same thing here, if we're moving at constant velocity. Okay, so then you could look at your y-coordinate. It's changing with time. As I move along this path, my y-coordinate is increasing. And my x-coordinate is also increasing as I move along this path. So I've got a delta y versus time and a delta x versus time. The rate of change of x, delta x over t, that's exactly equal to the x component of the velocity. So this leg of my velocity vector triangle, that represents the rate of change of the x component, how rapidly this x component is changing as we move along. And then this leg of the triangle, Vy, represents the rate of change of the y component, the y coordinate, as we move along. Now, if we're moving at a constant rate, that means that our velocity vector has a constant magnitude and a constant direction. So the hypotenuse is staying the same length, the angle is staying the same. Therefore, both legs of the triangle must be constant also. So Vx is constant, Vy is constant. Our x-coordinate is changing at a constant rate, and our y-coordinate is changing at a constant rate. Therefore, if you want to plot x versus t, where Vx is a constant, that's the equation of a linear graph. Same thing for y direction. If Vy is a constant, then y versus t, that's going to be a linear graph. I've got examples of those two graphs right here. Here's our y-coordinate versus time, and here's our x-coordinate versus time. Both of these graphs will be linear. If we pick two random points on our y versus t graph and calculate the slope by taking delta y over delta t, that's the slope. Oh, but that's also the definition of the y component of our velocity. Therefore, the slope of this graph is equal to the y component of velocity. Likewise, the slope of this graph is equal to the x component of velocity. So if you measure the lengths the lengths of the legs of our velocity vector triangle, Vx will be exactly equal to the slope measured on this graph, and Vy, the y component, will be equal to the slope measured on this graph. Let's compare these two graphs for a moment. Notice this slope is shallower than this slope, indicating that our y-coordinate is increasing pretty slowly compared to our x-coordinate, which is increasing, our x-coordinate is increasing more rapidly. You can tell that from looking back at our map here. Our path is directed more in the x direction than it is in the y direction. Therefore, our x-coordinate is increasing with time more rapidly than the y-coordinate is. Okay, let's look at some more of these maps of objects moving in straight lines at a constant velocity and try and match up graphs like this with pairs of graphs like this. So if you were to see this graph, could you match it to the corresponding y versus t graph and x versus t graph? I've got 4 examples. Zoom out, get this whole thing in frame. There we go. Okay, so 4 graphs of objects moving at constant velocity, each with a starting position, and then you see the direction that it's moving. So in a straight line at a constant speed. And we'll say that the starting position is when t equals 0 for each of these. So can you match this graph to one of these 4 pairs of graphs? I want you to think about, as you move along this line, is your x-coordinate increasing or decreasing? Is your y-coordinate increasing or decreasing? And is each one increasing rapidly or increasing slowly? Answering those questions should help you figure out which pair to match to each one of these. Okay, I'm going to pause the video, give you a moment to think about that. Ready? Okay, let's go over them together. This first one, as I move along this path, my x-coordinate is increasing the whole time. And as I move along this path, my y-coordinate is increasing the whole time. So we need a pair of graphs where y is increasing with time and x is increasing with time. That matches paragraphs B right here. Notice also that y starts at a slightly negative value, x starts at a more negative value at t equals 0, and that matches our behavior here. At t equals 0, y starts slightly negative and then increases. Here at t equals 0, x starts slightly or more negative and also increases. And note that the slopes of these two graphs are the same, indicating that Vy is equal to Vx. The y component of velocity is equal to the x component of velocity. And that's true because our path here is making a 45-degree angle to the x-axis and to the y-axis. It's moving equally in the x direction and the y direction. Next one. Here, as we move along this path, our y-coordinate is decreasing with time, and our x-coordinate, oh man, this gets tricky. Our x-coordinate is increasing. Oh. X-coordinate is increasing with time. Got it. Okay, x-coordinate is increasing, but more slowly than the y-coordinate was decreasing. Y is decreasing rapidly, x is increasing slowly. Which paragraphs matches that? Here we have y decreasing pretty rapidly and x increasing kind of slowly. Therefore, it matches set A. Notice also our starting points. At time equals 0, our x-coordinate is 0, but y-coordinate is positive. Here time equals 0, y-coordinate is positive, x-coordinate is 0. That matches as well. Next one. Here, as we move along the path, our x-coordinate is decreasing and our y-coordinate is increasing. Oops. Increasing. X is decreasing rapidly, y is increasing slowly. That matches this paragraph right here. X is decreasing rapidly, y is increasing slowly. Y-coordinate starts at 0 at time equals 0. X-coordinate starts positive at time equals 0. Looking at these two motions, we see that the only difference is that we're just sort of flipped over the x-axis here. So our x-coordinate is still decreasing rapidly. This time our y-coordinate is decreasing slowly. That matches this paragraph right here. X decreasing rapidly, y decreasing slowly. If we compare these two graphs, we see that they have the same slope, indicating that Vx, the x component of velocity, is the same for these two. Our x component of velocity is the same here and here. Comparing these two graphs, we see that they have the same slope, but just one is negative of the other. So this graph, y is increasing slowly, here it's decreasing slowly. So this Vx would be the opposite. This Vx, the slope here, would be the opposite of this Vx, the slope here. Here, I should be saying y. This Vy, the slope here, is the opposite of this Vy, the slope here. Here our Vy is small and positive. Here our Vy is small and negative. So that's graph 2.